Mohammad Javidian, and I'm a postdoc at the Purdue University. I got my PhD from University of South Carolina. My advisor is, my PhD advisor is Dr. Valtorta. I'm sure you know him. And I worked very closely with Dr. Jamshidi for some of our recent researches. And the fact that I want to present today is one of our recent work on using the causal inference in transfer learning. And hopefully this gives you some idea that how can we exploit causal inference in machine learning techniques, especially for transfer learning. Due to the short notice that I received yesterday, I have not prepared any specific presentation for this talk. So maybe I'm jump around some different slides, but I try to give you a high-level sense of the work first, and then I will go through the details. And please let me know if you have any question. You can type your questions in the chat box, or you can raise your hand or turn on your microphone and ask me directly if you have any question. So let me share with you the screen. So the work that I want to talk about today is robust causal transfer learning. We submitted this paper recently and it still is under review. But let me give you some motivational examples first, and then we go through this paper. In this scenario that you are looking at, we have different pictures of cows and camels. And if you look at these pictures, you can see most of these cows, the background is background of the in this picture, and the color of the camel more or less is brown. Assume that our task here to classify cows and camels based on a data set, which is a set of pictures of cows and camels. Just imagine that the data set that we have, almost all of them follow the same theme that you are looking at right now. And we train our algorithm based on this type of data set. And we want to use and deploy this trained model in a new environment for a new data set to classify and distinguish between cows and camels based on the machine learning algorithm. However, if we use just this type of data set for the prediction and classification task. And the test task, the test environment, if the test environment be different from the training environment, I mean, as you can see here, the background of this camel is green rather than a desert, or the background of this cow is a desert, more or less. And the color of the cow is black and rather than to be a black and white like the training environment, here is brown. So very likely our algorithm or our model, machine learning technique, fail to or classify correctly in this new environment. And the reason is that the algorithm, when you use the machine learning technique algorithm, the traditional and classical machine learning techniques, very soon these techniques find that highly relevant background to the type of the animals that we have here. I mean, if we train in this type of backgrounds, the machine learning techniques very soon find out that, okay, those backgrounds that are green, more or less, there is a cow there, and if there is a desert, is a camel there. So using this kind of training somehow mislead the model, and as a result fail to correctly predict or classify the and distinguish between the camels and cows. This is a very simple story, but you can generalize this simple scenario to many, many real world problems. That there are some background, or we call them context variables, that differ across domains, across environments. By domains and environments, I mean training environment and testing environment. More or less, when you try to use a machine learning technique, you train the model in a specific data set, and then you try to use that model for the prediction in the new environment, and mostly untested environment. So you should take it in account the differences between the context that you train your model and the testing environment. As another example, let me talk about this example, which is more abstract than the previous one. In this example, we have a context variable C1, C4 context. And we have three other variables in our experiment. Those variables that are not the context variables, we call them system variables. So we have three system variables and one context variable. And what's the difference between the system variables and context variables? Context variables, as I said, are those variables that differ across different environments and domains. Or more formally, we have the shift distribution across domain for those variables, like the story that I told you. But in the test environment, we have a shift in the background. And you can see the background of these camels are green, and the background of this cow is a desert. Or even the color of the cow. These can be considered as a context variables that differ across environments and domains. So in this imaginary scenario, we have a context variable that across domains, we have a shift distribution for this variable, and three other system variables. And assume that we have trained this model in the source environment or training environment for the prediction of X3 based on the other variables in this scenario. Sorry, for the prediction of X2, for the prediction of X2. And as you can see in this example, there are two variables that are very highly relevant to this target variable X2, which are X1 and X3. And this is an imaginary causal graph. And by a causal graph, I mean all of directed edges in this scenario have a causal interpretation, which means X1, X2, there is a directed edge from X1 to X2. That means X1 is the cause of X2. And the same X2 is the cause of X3. So for the prediction of X2, if you use any classical machine learning technique, they use both X1 and X3 for the prediction of X2, because these two variables are highly relevant to the X2 in this scenario. However, if we have a data shift in the context variable C, and we use both X1 and X3 for the prediction, as you can see in the right figure, we have in the left figure, for the prediction of X2, we have used just X1. And you can see that, okay, the prediction is not very accurate, but it's somehow noisy, but it's maybe acceptable. But if we use X3 for the prediction in the testing environment, you can see that the very bad prediction in this figure, and we have a huge data shift here, and that shift leads to the very bad prediction. So if I want to summarize this story, the main goal here is to find some subset of variables in our experiments that make our prediction not only accurate, but also robust across environments. And by robust, I mean even by having shift in the context variable across environment, that subset that we are using should be able to give us a good prediction. So in order to formalize this problem in the context of causal inference, you need to have some background related to the causality and Bayesian networks. But I try to give you some basic information about the causal graphs and d-separation and DAGs first, and then we can go forward and talk about the details more. Let's start with the definition of a causal graph or a DAG. A DAG or directed acyclic graph is a directed graph, is an acyclic graph, which means there is no cycle, directed cycle in this graph. So a DAG is a directed acyclic graph. And most of the time, a causal graph is shown by a DAG. We have a notion about the DAGs that we call them d-separation. You can imagine three different connections in a DAG. The first type of connections is a serial connection. As you can see here, A is directed connected to B and B is directed connected to C. In this type of connections, serial connections, if we have evidence for the intermediate in the node or variable, you can say, here, the knowledge or the evidence about the variable in the middle blocks the connection between A and C. For example, you can say that the season, consider that A is a variable about the season, like the fall, spring, winter, summer. B is a variable about the status of raining. It's a binary, it's raining or it's not raining, false or true. And the C is the, like say, the street is wet or dry. This very simple imaginary scenario. And without having any information about the raining status, there is a connection between the season and the status of the dryness or wetness of the street. For example, if the season is summer, more likely is not raining, and more likely is the street is dry. Or if it's winter, more likely it's raining and more likely the street be wet. But in this story, if you have evidence about the raining status, that disconnect the season from the effect of the season on the street. For example, if it's raining, doesn't matter that it's summer or winter or spring or fall. you can tell that the street is wet. Doesn't matter that what's the season. So, or if it's not raining, it still doesn't matter that what's the season right now. Very likely the street is dry. So in a serial connection, in a DAG, when you have evidence on the middle variable or node, that evidence blocks the path between the beginning of the serial connection and the end of the serial connection. Or technically, we call that B separates A from C. Separation, which means, or blocks, like blocks here. But the D separation is used because this graph is directed. So the D separation notation is used for the DAGs because of the directed acyclic graph that we are working on. So the first type of the connection is a serial connection. And in a serial connection, conditioning on the middle variable or node separates the endpoints of that connection. The second type of the connection in a DAG is a divergence connection. So you can see that a divergence connection in this figure, and the same as the serial connection, having evidence on A blocks the connection between B and C and between B and E and so on. Or technically, we say that conditioning on A separates B from C, also separates B from E and E from C, and so on. The third type of connection is converging connection, which is the opposite situation of the diverging connection. In a converging connection, the story is completely opposite. Conditioning on A connects B and C, also connects B and E, and C and E. Remember that in the diverging connection, conditioning on A blocks the connection between B and C and B and E. Or conditioning on A separates these variables. But in the converging connection, conditioning on A connects these variables. So in order to separate B from C, we should not conditioning on A. Or without conditioning on A, we say that B is marginally independent of C. Or B is marginally independent of E, also for the C and E. So these are three types of connections and these separations that we need to use formally in our case. And as you can see here, what's the reason that using X3 makes prediction bad? By the explanation of three types of connection that I explained to you, you see the connection between C1 and X2 is a serial connection. So conditioning on X1 blocks the path between C1 and X2. or conditioning on C1 deseparates C1 from X2. However, the connection between C1 and X2 is a converging connection, the third type of connections, which means without conditioning, these two are marginally deseparated or independent. However, conditioning on X3 makes this connection open, which means when you are using X3 for the prediction of X2, technically you are conditioning on X3 and you are opening the connection between C1 and X2. And when you have a data shift when you have a shift distribution in context variable, that shift, since this connection is open, directly affects on the X2. So that makes the prediction bad. So right now you should have a better sense about why using X1 is better than using X3 for the prediction of X2 in this scenario when you have a shift distribution on context variable C1. Okay. Let's give you another motivational example that we use in our paper. In this simple scenario, we have some patients that we want to test them for the diabetes. And we gathered some symptoms and we asked them some questions to have some clinical data. And we asked them about their age, about the status of delayed healing, partial paralysis and weakness and blurred vision. And in this story, you know that when a person suffers from the diabetes, they suffer also from the blurred vision. Their vision, these kind of people more likely have blurry vision. And when the condition is serious about the diabetes, these people also feel they are weak and they cannot do their normal activities. And also they realize that their wounds heal takes a lot of time to heal their wounds. So delayed healing also can be seen in the diabetes people, and also the partial paralysis. However, in this story, we know that all these four factors are directly affected by age of the person. And the correlation or relationship between age and these four factors is when the age goes up, more likely the people suffers from these symptoms. These symptoms show up in these people. if you assume that the causal graph in this scenario is like this one that you are seeing in figure A, you know that like the previous example, the connection between age and diabetes is a serial connection for uh, uh, these blue uh, symptoms, variables. But is it converging connection between age and diabetes that these variables are in orange. And this means these two variables, weakness and blurred vision, are the symptoms of diabetes. But these two variables, as you can see, could cause some problems in the body that makes the failure in the pancreas and make the people diabetic. So in this story, we gather data in two different categories for young people and for old people. And in this story, we use the threshold 50, I believe. Yeah. We divided the questionnaires in two categories. So we have two different environments. One for the patients is less than 50 years old, and old patients is more than 50. And we trained, if the same thing happened here, you can see in the diagrams at figure 1b, you can see the distribution of these factors and the density distribution of diabetes. And by changing the age category, you can see we have a big shift for all of these variables across environment. You can see that, for example, the delayed healing, we have a big shift. Also, we have a very big shift about the blurred vision between the young patients and old patients. Also for other factors. So what should we do in this case? And we verified that since this is a causal graph that we have for this scenario, we shouldn't use weakness and blurred vision for the prediction of diabetes across these two environments at least. Since using those variables make the connection between age and diabetes open, and that means by shifting the age across environment, that effect on the prediction of diabetes dramatically based on this shift distribution in age. So it's better to just use these two variables that are the cause of diabetes, first of all, and second of all, using these two variables makes the connection between age and diabetes blocked, and or technically these two variables separates age from the diabetes, or as we like to say, using these two variables are causally invariant features across source and target environment. Since these two are causal effects of diabetes, and also using these two variables do not allow the age to affect on diabetes directly. So by changing the age across training and testing environment, we have a better prediction for diabetes people if you use just these 4 symptoms. And the results in our experiments confirm this observation. If we use all of these variables, the mean square error is 0.29. But if we use just these 2 blue factors for the prediction, is 0.221, the minimum, the mean square error. This is the whole story that I told you in high level. And I think it's clear right now that in our story, the main task is when we have a data set, finding those causally invariant features that make prediction robust across source and target environment. This is the main problem that we want to solve. Here is most of the time we do not have the causal graph or the causal model of our experiment, or learning those causal models or causal graphs is difficult, and it's a challenging task. So is it possible to develop an approach that without even knowing about the ground truth causal model in our stories, develop a sound algorithm or method that that helps the machine learning technique for the transferring the knowledge from the source to the target environment and have a better prediction or classification or any other task that we are interested in. This story. So, any questions so far? I didn't look at the chat box, but if you have a question, you can open your mic and ask me directly. If you don't have any question, I'll go forward. Okay. So let me talk about the formal yes. Okay. for predicting T, which is a target variable, from a subset of features, S, that are system variables of all features, rather than the context variable and target variable. So we want to find some features of this subset of all features that makes the prediction robust across domains. And by robustness, I mean we should have a lower bias, which we divided to two different metrics to estimate the bias in our estimation, the transfer bias and incomplete information bias. So the total bias is the summation of these two biases that we have in our scenario. And there are some assumptions that are very important in this case. And let me tell you about these assumptions first. We have two main assumptions, the Markov condition and faithfulness assumption. The Markov condition simply says we have a DAG, a directed acyclic graph, and a probability distribution that is defined on the variable or nodes on this DAG. So simply any d-separation in the DAG implies the independency in the data set. Remember that I told you in many cases, we do not know the ground truth causal model. So when you do not have the DAG, so you need to learn the DAG, or you have an approach that satisfies these two assumptions. The first one is if there is a d-separation in the DAG, that d-separation implies an independence relationship in the data set. And the faithfulness assumption is the other way around, which means any independence or dependence relationship in the data set should be reflected in the DAG as well. So there is a one-by-one relationship between the independency and dependency between the DAG and between the data set. And so our first assumption is our experiment is based on some hidden or unknown causal model. But even without knowing the causal model, we know that ground-truth causal model satisfies, our experiment satisfies these two assumptions, which means any independency in the data set implies a d-separation in the DAG and vice versa. So one of them is Markov condition, another one is called faithfulness assumption. Another assumption that we made here is causal sufficiency assumption. A causal sufficient assumption means when you have two variables that are causally related, for example, in this simple example, smoking is a cause of the cancer in this scenario. You are assuming that there is no unmeasured common cause or unmeasured hidden variable in this scenario. If you assume that there is no unmeasured common cause or unmeasured selection bias, you are assuming causal sufficiency. But in reality, it's quite possible that there are some hidden variables that affect both variables that are causally related in your case. For example, here, maybe there is some unknown gene that affects smoking and also the cancer, lung cancer in this scenario. But you don't know about it or you cannot measure it. If you do not assume that there is some unmeasured, U for unmeasured, common causes in your scenario, so you are not assuming causal sufficiency. In our case, in our paper, we do not assume that the causal sufficiency assumption, which means it's possible to have some unmeasured common causes. And unmeasured common causes sometimes is called confounders or hidden variables. So it's quite possible to have some hidden variables. But also there are some more assumptions that we need to make to build an algorithm to find the causally invariant features across domains. So it's quite possible that in this scenario may have some hidden variables. Another one, our data set satisfy the Markov condition and faithfulness assumption. And finally, we assume that there is no direct edge from the context variable toward the target variable. Because if there is a directed edge from the context variable and target variable, you cannot use other factors or features to de-separate the context variable from the target variable. It's useless to use other features to de-separate context variable from the target variable. So it is crucial to assume that there is no directed edge between the context variable and target variable. This is one of the limitations of our work. And another one, also there is no direct edge from the, so none of these features and system variables be the parent of a context variable. These are two more limitations that we have and by having these assumptions, now we are able to design an algorithm to find the causally invariant features across environment. So, as I said, since we can have some hidden variables in our study, we need different type of graphical models rather than DAGs that also can be able to cover the unmeasured confounders and hidden variables. And this type of graphs is called acyclic directed mixed graphs. And the difference between them and the DAGs is possible to have a bidirected edge in this scenario. And when you have a bidirected edge, the interpretation is there is a common causes that it's hidden in your study. So you cannot, or you do not want to represent it explicitly. So since we have if you have a common cause, which is hidden, you can use a bidirected edge between variables. So the difference between acyclic directed mixed graph and DAGs is we have two types of edges, directed and bidirected edges. And the main concept that can help us to find the causally invariant features is a very famous concept in the causal inference literature, which is called Markov Blanket. Let me talk about the Markov Blanket quickly. In a DAG, if you want to find the Markov Blanket of a target variable, simply a Markov blanket in the machine learning context means those variables that are highly relevant to that target variable. As you can imagine, those variables that there is a directed edge between them and the target variable should be in the Markov blanket. But it's possible to be more than just those variables that are directly connected to the target variable. So the elements in a Markov blanket consists of three different subsets. The parents, you can see here, C, F, G, that are directly connected to the target. The children, those elements that there is a directed edge from T toward them. And these type of variables also are directly connected to the target and expose of the target variable. And what's the reason of the expose to be in the Markov blanket in DAGs is since the children are already directly connected to the target variable by conditioning on a child of a target variable, you are opening the connection between T and this L. So these type of nodes are called exposes. And the reason is because T and L are sharing a child. So technically, L is an expose of T. And all of them together, parents, children, and exposes, make the Markov blanket of T. So we showed that in our paper that in order to find the causally invariant features across environment of a target variable, it's enough to just focus on the Markov blanket of the target variable. So as you can see here, there are many, many more variables in this story that are irrelevant to the target variable T. So what's the importance of using Markov blanket here? The first thing is reducing the search space for finding those causally invariant features. And by reducing the search space, you make your algorithm scalable. So, which is very important when you know that in practice, when you are working with the real world problems, there are sometimes thousands, hundreds, thousands of variables in your study, and you should find a way to make your algorithm scalable, and you have to speed up your algorithm in practice. So using some kind of brute force search, that doesn't make sense and it's not applicable. So in order for the purpose of feasibility of your algorithm and scalability, Markov blankets are very good candidates in this case. But this is a DAG. What about our case? You remember that in our case, we can have the acyclic directed mixed graph, which means we can have a bidirected edge as well. So as you can see in the figure B, we have some directed and bidirected edges here. And we want to find the Markov blanket of T in this scenario. We proved that those variables that there is a path between those variables and T, that each variable in between, there is a collider. What does that mean, a collider? You see, for example, between T and E, we have a converging connection. A converging connection is a collider. So, and remember that a single edge is also a collider path. So in acyclic directed mixed graphs, in order to find the Markov blanket of the target variable, you need to find those variables that there is a collider path between those variables and the target variable. So the variables in gray are out of the Markov blanket because there is no collider path between them and T. But A and B are in the Markov blanket of T. Remember that the single edges are collider path by definition. Also, D and C are directly related to the T, and there is a single edge between them and T. So C and D also in the Markov blanket. E is in Markov blanket, E is a spouse of T, and you can see that there is a collider path between E and T. Y1 and T, there is a collider path between Y1 and T, because we have a collider at C between Y1 and T. Y4 is in the Markov blanket because there is a collider path, Y4, Y1, C, and T. All elements in between, we have a collider. We have a collider at C, we have a collider at Y1. And so on, Y3, also Y3 and Y2. So in this way, we define the Markov blanket. Another contribution of our work is we proved that in a theorem that the first of all, we proved that for finding the causally invariant features, or finding the best separating set of features that de-separates context variables from the target variable T across is enough to focus a subset of a Markov blanket, just neighbors of the target variable. This is our first theorem. And in the second theorem, we define the Markov blanket of we prove that as I told you, those variables that there is a collider path between them and the target variables are in the Markov blanket of T and nothing more. This is the second theorem. And the third theorem tells us that the traditional or class standard Markov blanket discovery algorithms in the literature of DAGs also can be used in the acyclic directed mixed graph without any modification, which is great. In the DAGs, you know that we have the causal sufficiency assumption, because DAGs, when we have a DAG, we are assuming that there is no hidden variable or hidden common cause. But here we relax this assumption and we prove that still these algorithms are sound algorithms for learning the Markov blankets of the target variable in this case. And our algorithm is very simple. In the first step, we learn the Markov blanket of the target variable, and then we try and we search, we use it for makes the context variable independent of the target variable. If we find that subset, we return that subset and we use that subset for the prediction in the test environment. If we couldn't find, we return a failure that our algorithm cannot be used for the prediction of the target variable in the test environment. In order to evaluate the performance of our algorithm in practice, we use two different data sets, the synthesized data set and the real world data set. In the synthesized data set, we assume that, okay, somehow we cheat here, that we start with a ground truth causal model that we know it, and then we generated two different data sets, one for the source environment and one for the target based on this causal graph that we have here. And the reason is we wanted to verify that when we know the causal model and we know the real Markov blankets, and we know that what's those context variables, and applying some shift distribution on this context variable across source and target environment, using different methods, which one is more robust and more accurate in practice. And this is for the synthesized data set. And let me show you some of these. Yes. For example, here, we know that the causal graph is this graph, directed acyclic graph in figure A, 3A, and our approach is robust causal transfer learning, RCTL, robust causal transfer learning. And as you can see in this story, the minimum square error is less than the most of the other algorithms that we compared against in this case. And also is a scalable algorithm. For example, if we synthetically generated this this causal model and the data set in the test and target environment, and we tested in this case. And as you can see, also in this scenario, our RCTL algorithm shows a better performance in comparison with other machine learning techniques in the literature. Also, we evaluated our algorithm in a real data set for the diabetes, and we used the RCTL for the prediction of the diabetes across environments for the young age and for the old people, patients, and we got a better results in this case as well. That shows our approach is promising in not only for the when we know about the causal ground truth causal model, but also when we do not have any information about the ground truth causal model. It's still applicable, and the results seems promising. And as a future work, we plan to relax some of the limitations that I told you about this approach. For example, what about the cases that there is a directed edge from context variable toward the target variables? What should we do in these cases? And this is a very exciting project that we are working on right now. Hopefully, this gives you some motivation for your future work, and maybe if you're interested, you can talk to Dr. Jamshidi to join to our projects on using causal inference techniques for the performance analysis or improving the performance of machine learning techniques, especially for the transfer learning. That's all. That's it. Thank you all for listening, and let me know if you have any question.
Yeah, thank you, Mohammad. It was a great presentation.
Thank you so much. Any question? Any comments?
I'm here, but thank you.
Thank you for coming and listen to the talk. Cody, if you have time, please stay on the call. I want to talk to you, for 5 minutes, if you can do it.
Sure.